Embark on a journey of inspiration and discovery with the Purdue Lecture Hall series, proudly presented by the Purdue Institute of Inflammation, Immunology, and Infectious Disease. Join us as we delve into the remarkable odysseys of these aspiring scientists, each crafting their own narrative in the world of science and groundbreaking research. Take a glimpse into their diverse cultural backgrounds and the journeys that brought them to Purdue University. Thank you for watching the Purdue Lecture Hall series. Remember to hit the like button and subscribe to our channel. Welcome, everybody. My name is Tommy Soares. I'm the Director of Scientific Strategy and Relations for the Purdue Institute of Inflammation, Immunology, and Infectious Disease. And today on the Purdue Lecture Hall series, I have the pleasure of welcoming Dr. Venkata Are. He's joining us today from the Biological Sciences Department at Purdue University. He is a postdoctoral research associate working in Dr. Richard Kuhn's lab and has been at Purdue since May 2021. Venkat has a background in structural functional characterization of Aminopeptidase-P fold proteins from Devi Ahilya University in India. I hope I didn't butcher that. His work now focuses on the structural elucidation of dengue virus, attachment factors, and receptors using Cryo-EM. Venkat's passion extends beyond the lab. He's also deeply involved in farming and cooking. His unique journey bridges the gap between structural virology and practical life sciences. Let's dive deep into his insights. Welcome to the program, Venkat. Thank you so much for taking time to tell us a little bit about your journey and tell us a little bit about your research as well.
Yeah, thanks, Tommy, for kind introduction and inviting me for the Purdue Lecture Hall series. So it's a pleasure to have in the Purdue Lecture Hall series, and I would like to share what I have done in the my PhD and what is my farming area, little bit about, and
Perfect.
who is my inspiration for doing all this, and
I love it.
what I'm working right now in the viruses in the Dr. Kuhn's lab. All this I will cover one by one, step by step.
Perfect.
As my title is that I'm going to talk about today dengue virus attachment factors and receptor protein structures with dengue virus whole complexes and how these important for the virus entry into host cells. So as I mentioned, so I'm going to talk about first, as Tommy said, I'm allowed to do the farming and other activities. So I would like to share first my farming activities. Here I do farming in the right figure in 2020. I think before I came to US, I was doing farming in my farmland. So you can see here, we have a small farm like 4 acres right now. And we used to use these bulls for doing plowing and flattening the land, different activities. We don't use as the tractors for doing the farms because of maybe we have only 4 acres of land. It is not sustainable, so we use these bulls and we do all these farming. Here I am the one who is doing farming, and the right side figure is the my farmland, which is having the sunflower crop. Here this is 90 days crop. We get the oil seeds from this sunflower and make the oil and uses for the cooking edible oil, like the way here uses the canola oil and other oils for the cooking purpose, olive oils, but we uses the groundnut oil and this sunflower oil for the cooking purpose. So after this, we also cultivate, apart from the sunflower, groundnut, we do many different variety of crops, around maybe 20 30 crops. So here the right side, again the right side figure is the rice crop in the same land. In the alternatively we rotate the crops. So here you can see the rice, generally GMO crops comes up within 90 days of period, but these normal crops comes up to 150 days. So at the end of this crop, you can see this kind of golden color rice grains. This is the mature stage, so we can harvest now and use these grains for the making the rice. So in the same land 2 years back, what we have done, because of we have my parents are getting older and older, so they are not able to work full time, so we change it to farmland of cultivation land into the fruiting trees, and we put these guava and coconut plants and different variety of fruiting plants. Now this is 2 years back picture, and here you can see these guava plants are becoming big now, and we are yielding guava fruits, and these are right now in market, and we are selling per kilogram of guava in $0.2. It is too cheaper compared to here. We are buying here guava fruits in a India market or wherever we go, and we buy even in the Meyer also. We are buying it per kilogram of the guava in $10 to $15. So it is a huge changes in the price range. Here there is a coconut plant. Coconut plants are 2 years old, but no, we need to wait for another 1 year to yield this kind of coconut fruits. This is what my brief introduction about the farming. Right now I would like to share about who is my inspiration. So here is my grandmother, who is she is crossed 95 years old, still she works in the farm. She has very bad story in her life, and she is the major motivation for me all the time, because my grandmother and grandfather has 6 children, and grandfather was died with throat cancer, and the 5 of the children were died with uh, passed away with pits and murcha is the Telugu word. With those diseases, lack of awareness of the medical as well as help and medical emergency conditions, she lost her husband as well as 5 of the children. She left with only my father. At the age of 13 years, they all are died in the 9 to 13 years age group. They were sad. My grandmother and father was sad in one of the festival, and then we all four children asked him what happened, why you both are in the sad mood. Then they shared me all these story. Then I was in the nine years old that time when they said all this story, that somehow imprinted in my mind to do something in science. At that age I don't know like what is science and how to do science. Like I thought I can do something for this disease, but it is not true. Afterwards, when I growing bigger and bigger and in the science field, when I enter into the science, I realize science is vast field and it is not easy to do by one person. It is a collective field of collectively we have to do gather the information, do the science. That's what it works. And here is my mom and dad. He lost his parents father at the age of 13. Still he grown up with his mom, and they both were growing family. My father, now my mom has 4 children, me and my elder sisters, 2 of the elder sister and one younger brother. He used to have only zero point 0.3 acres of land, and yearly his income is $1,000. Yearly income is $1,000. Still, he has to educate all 4 children, and he has to expand his farmland. That's where I learned his efforts and constant hardworking, and his micromanagements for growing family as well as farmlands. So he is my inspiration for my management the things in the micromanagement level, macro management level, and what is the upcoming future directions, prediction of the environment, and based on that he put the crops and other things. So here is another legendary person who is my inspiration. He is a Dr. Bhattacharjee, who is a retired scientific officer from the Baba Atomic Research Center. My MS teachers as well as my PhD mentor introduced me this Dr. Bhattacharjee, and I stayed him from 2013 to 2022. He is no more. He passed away in 2022. Still, 2022 from 2013, he used to motivate me all the time. He used to narrate me all the scientific stories and how science work. Even he used to tell me about the Watson Crick lifestyle and biography. He taught me all the scientist biography first, how they struggled and how they entered into the science, and how they find out these specific novel things. All these he used to narrate me those things even in the weekdays or weekends. Every day night he used to taught me, like from dinner hours we used to sit together on the dining table. It goes on every day. Like he used to taught me a lot. He is the my major motivation for the science. After completing my MS, I was thinking to change to my direction from science to IT sector or some government jobs to earn money and support the family. But he said, constantly you work on the science, you will get the recognition as well as the good lifestyle, and you will get a good recognition in the science. It's your major interest also, so continue in the science. Don't look here and there, so that it will not the standard fields other than. So work on the science. These are the four people are my major motivational motivation. And my mom is also work along with my father equally in the field as well as house. They both are illiterate. Like my father completed fifth standard, and still he is not able to read the newspaper. He reads Telugu newspaper but not full fledged. But he knows the importance of, both of them knows the importance of the education. That's why they equally educated all four children, and we all are in the uh, science. One is in the chemistry, two of them are in the chemistry, one is in the biological science, one is in the mathematician, like that. So these four people are my inspiration. So now I will talk about where I did my MS and where I did my PhD and my PhD work in the coming 4 slides. So I completed my master's from the Devi Ahilya University School of Biochemistry in the School of Biochemistry. So in 2013, after 2013, I joined the PhD in the collaboration with the uh, School of Biochemistry, Devi Ahilya University, and the Rajaramana Center for Advanced Technology, where we have a single synchrotron in India, that is in the central India, Indore, where here it is the synchrotron outer picture or the building. So you can see he have one protein crystallography beamline and associated biochemical laboratory. So there I work completely 4 years for my PhD, all the time in the protein crystallography field completely. So I work in this protein crystallography in the aminopeptidase P fold proteins. Aminopeptidase P fold proteins, these are the group of proteins which has a similar structure. Their functions are different. They have aminopeptidase activities and carboxy like peptidase activities. You can see here. So when we take the any protein diet, our proteins are recycling in our body. Generally proteases and peptidases act on those proteins and forms the free amino acids. Those free amino acids are useful for the recycling or resynthesize the proteins in the body. So out of 20 protein coding L amino acids, we have a peculiar amino acid, that is a proline, which has a side chain of the cyclic ring, that is prolyl ring. So that binds to that forms the immunopeptide bond with N-terminal amino acid. So this immunopeptide bond is not cleavable in the N-terminus and carboxy terminus of the proline. So those bonds are cleaved by the aminopeptidase P-fold proteins, proline specific proteins, and XAPRO dipeptidases, and XAPRO dipeptidyl peptidase 4 and 2, and prolyl endopeptidase P, and prolyl carboxypeptidases. These are the enzymes which cleaves these bonds and free of these amino acids, and recycle these amino acids for the synthesizing the native another new proteins. So here you can see the aminopeptidase P fold proteins, how they look like. Here they have a two domain structure. One is at the N terminal domain and the C terminal domain, and the C terminal domain itself has a substrate binding site as well as metal binding site. These are the metallopeptidases. Metallopeptidases, they require divalent metal ions, whether manganese or any divalent metal ions for its activity, but they show maximum activity in presence of manganese and zinc. So this is the structure which I solved from the Xanthomonas campestris hexapro dipeptidase. This Xanthomonas campestris causes the citrus canker disease in the lime plants. So this structure, this protein forms the homodimer. We can see here the homodimer is majorly stabilized by the N-terminal domain interactions. So the N-terminal domains are interacted, and these C-terminal domains are slightly apart, and they don't have direct contacts or direct interactions. The major interactions are N-terminal domain interactions. So these are the strictly dipeptidases. Due to our length of this presentation, I reduce the, I'm not showing the any activity assays for these enzymes, but structurally they look like these are the dipeptidases. So another bacteria is from the Deinococcus radiodurans. Deinococcus radiodurans is survive even in the high radiation resistant environment. It survives up to 6 kg radiation resistant. It can resist up to that kilogram. Then this bacteria has another class of Deinococcus radiodurans hexaprodipeptidases, which has extra loop at the neck region between connecting region of the N-terminal domain and the C-terminal domain. This structure, this dimer, it exists as a dimer. The dimer has interacted with the N-terminal domain interactions, but the C-terminal domains are far apart compared to a previous structure. Previous structure, it is in the globular shape or closed conformation. This one is a fly. When the flies are birds flying, the wings are open. The same conformation here. If you see the N-terminal domains, you can compare as a body part, and these two are the wings. They are opened up from the N-terminal domain. So even when we do the molecular dynamics, these C-terminal domains comes close to the N-terminal domain and forms the active site in the closed conformation. This is also strictly a dipeptidase. It cleaves the hexaprodipeptides into the free amino acids, so proline and X, any other amino acid from the N-terminus. So here it looks like another same structural proteins from the Escherichia coli and Deinococcus radiodurans. It looks similar compared to previous two structures, but these are the aminopeptidases. These are also metallopeptides. These are the metal ions in the C-terminal domain. Their activities are they digest the longer peptides than the dipeptides more efficiently, and it has dipeptidase activity is less, and a longer peptides are more prone to digest and releases the free amino acids. Here this DXRY motif, which is important for stabilization of the longer peptides in its active site, and digest the N-terminal amino acid, releases the N-terminal amino acid from the proline. So these two enzymes also do the same kind of function. They have a similar kind of structure compared to previous two structures. Here another structure from the plant, which is Cicer eritinum, which is like equal to spinach. We call it, maybe it is in the spinach scientific name is Cicer eritinum. No, it's Cicer eritinum is something different, so not the spinach one. So here it has a similar kind of structure. This is from the spt16 N-terminal domain. Spt16 is a suppressor TY16 protein, which is a part of the FACT complex, facilitated transcription association complex. So it has a multi-domain complex. One of the domain is N-terminal domain. It has a two-domain structure. Again, the peptidase activity, peptidase domains structures. You can see N-terminal domain and C-terminal domain. It exists as a monomer. It's not a dimer, or it's not interacting with any other domains of the structure complex. So it directly interacts with the histone complexes, nucleosome complex H3H4 histones, not the peptidase activity. It won't have even conserved metal binding residues. It directly interact with the H3H4 histones in the nucleosome complex. While replication or mutation repair, repairing the DNA, or it's in the involving in the unwinding the DNA complexes and rewinding the complexes, those mechanisms. Here here you can see in our pull down assays, so spt16 protein bound on the base, washed with excessively with buffer, and we put the H3H4 histones, and then excessive proteins was washed. Then we eluted proteins whole complex from the beads. You can see spt16 ciceretinum protein with H3H4 histones. Completely it is interacting directly with H3H4. This is what I have done it in my PhD. In briefly, I have cleared. So now onwards, I'm going to talk about what I'm working in the Purdue in the research lab, what is like in the field of viruses, and what virus I'm working, and how these viruses are entering into the body, and what are the different types of viruses. On all these information I'm going to present now. So what is virus? Viruses are the infectious agents, are submicroscopic infectious agents which requires the living cell for its replication, and it infects all forms of life, plants, animals and bacteria like prokaryotes and prokaryotes, eubacteria and archaebacteria. It contains a segment of nucleic acid, either it is a DNA or RNA, nucleocapsid core proteins. These are the non-enveloped viruses. This is the simple structure of the non-enveloped viruses. Their size is smaller than the enveloped viruses. Enveloped viruses has the same nucleocapsid genetic material or the nucleic acid, and surrounded by the nucleic acid core proteins, and the lipid bilayer and the spike proteins are the envelope proteins, which is surrounded on the lipid bilayer. So you can see this is enveloped virus, we call it as. Based on these structures, viruses are not classified. You can say different class of the viruses has a similar kind of structures, similar kind of shapes, but they were not in the under one class. You can see here. Hmm. You can see here I put many different structures and with different viruses. These are the enteroviruses. They are in the icosahedral symmetry, and which is a non-enveloped virus which has a positive sense RNA virus. It causes the different human diseases, but these are the simple icosahedral symmetry viruses. Hepatitis B is again, it is a double-stranded DNA virus. It has a lipid bilayer and the envelope proteins and nucleocapsid core, and it causes the liver cirrhosis. And again, another third virus is the rabies virus. Rabies is the helical, like this is a native sense RNA virus, uh, and coated by the nucleocapsid protein and helical symmetry rod shape or bullet shape virus. The lipid bilayer is anchored with the envelope proteins. Then we all know about the SARS. It is wondering about this world from last 3 4, like from 2019 to up to 2022, or currently also it is still there, so everybody knows about this. Then this HIV virus is again negative strand RNA virus, segmented RNA virus, which has a nucleocapsid core in the conical shape, and nucleic acid core and the lipid bilayer and the envelope proteins are in the spherical form. Envelope it has a GP120 and a GP41 proteins are in the envelope. Adenoviruses are the naked viruses, which is again in the DNA viruses. You can see these nucleic acid core and the nucleic acid and the spike proteins. These are the filoviruses. Filoviruses are the filamentous viruses, like in Ebola and Marburg viruses fall under the filovirus class, and they are in the they have a filamentous shape or structure, and their lengths are varies, and the diameter is around 80 nanometer. So it is very severe disease. It causes the hemorrhagic fever, and its mortality rate is more than 50%. So you can see different viruses, all of them has, even though shapes are different, their genomic materials are different. So even based on these the shapes and structures, we can't classify them. So here in the, as per the Baltimore classification, viruses are classified into the 7 groups. Each group has, based on their genomic material, standardness and sense of the DNA and method of the replication, they all grouped into 7 groups. So you can see double-stranded DNA viruses, single-stranded DNA viruses, double-stranded RNA viruses, single-strand RNA viruses with positive sense RNA, single-stranded RNA viruses with negative sense RNA, double-stranded DNA virus with reverse transcriptase activity, single-stranded RNA viruses with reverse transcriptase activity. So we have many different family of viruses in under the each group. So out of all these groups, currently I'm working on the Flaviviridae, which is a single-stranded RNA viruses, positive sense RNA viruses in the Flaviviridae. As I mentioned in my title, I'm going to talk about the dengue viruses. So flavus means in the Latin yellow. Yellow fever virus was the first identified virus in this family and group. Based on that, it causes the yellow jaundice in the victim. That's the name where it comes. So envelope, these are the envelope positive sense RNA viruses. They have around 10.7 kilobase pairs of RNA as a genomic material. They code the single polyproteins, and the size of the virus is around 50 nanometers. The polyprotein is processed by the cellular and the viral proteases into different structural, non-structural proteins. These flaviviruses has 3 structural proteins. One is capsid protein, PRM, precursor membrane protein, and envelope protein. And these are the non-structural proteins from NS1 to NS5. So you can see when it is replicated in the or translated in our cytosol, in our host cytosolic cell cytosol. So this protein embedded into the membrane, then it acts by this NS3 is a viral protease, and these signal protease from the signal peptidase from the host cell, and the in the Golgi there is a one more furin protease, which cleaves the PRM into PR as well as M proteins, two different segments. So they all assemble and forms the virus, and they come out from the cell and infect the new cells. That's the way it works. So here, how these viruses are transmitting from one species to others, how these viruses are transmitting. So around 70 viruses are grouped under these flaviviruses. We can see that some of the viruses are transmitted by the Culex mosquitoes, and some of them are Aedes mosquitoes. Some of them are transmitted by the ticks. Some of the virus vectors are unknown. So you can see here West Nile virus, Japanese encephalitis, St. Louis encephalitis viruses were transmitted by the Culex mosquitoes. Dengue viruses and Zika virus, Sponvinia virus, yellow fever viruses are transmitted by the Aedes mosquitoes. Tick viruses are the tick-borne encephalitic virus. Powassan viruses are transmitted by the ticks. These are the vectors for known viruses. I'm going to talk about the dengue in the current talk. So here there are many structures are known from these flaviviruses, different virus structures like Zika virus, which is outbreak in the 2016 and solved by the Richard and Michael's group. Here you can see the structure of Zika virus, and here there is a TBEV, tick-borne encephalitic virus, and the West Nile virus and dengue 2 viruses structures was already solved, and we can see, but none of the virus structures from these flaviviruses, how these viruses are enter into the human body or host cell, what is the attachment factor, what is the receptor, exactly not known still now. So that's where I work, and here so we can see those in the briefly. So these all look like a same structure wise, but they have different sequence similarities, and they have different sequences on the table of proteins. That's why they affect on the each of them select the specific host and specific cell type where it infects, and the specific vectors for the transmission. So here yellow fever viruses are majorly distributed, are endemic in the Middle East countries and the South American countries. So here Zika virus also in the South American countries, Middle East and Eastern countries. So West Nile is also present in the North American countries and part of South American countries and the Middle East and Eastern countries, even up to Australia. So Japanese encephalitis is present in India and Eastern countries. So these are the 4 viruses which are endemic areas in the world. So I will say in the couple of slides later, after 1 or 2 slides later, where the dengue virus is endemic and throughout the globe. So I would like to introduce now dengue virus. What is dengue virus? Dengue is causes the dengue fever. It currently there are 4 serotypes circulating in the society. They grouped under the flaviviruses and the family Flaviviridae. Yearly 400 million cases are reporting. 100 million cases are shows the clinical symptoms. 500 cases are severe dengue cases. So the symptoms of this dengue fever is the mild fever, nausea, vomiting, rashes, muscle and joint pains. Severe symptoms are the dengue hemorrhage fever and dengue shock syndrome and plasma leakage. There are 2 vaccines that are available, right? This dengue vaccine was produced by the Sanofi and FDA is approved. They have certain limitations. Their efficacy of this vaccine is low, and they recommended to give this vaccine from the 8 to 16 years age group children, and it shows some ADE or some symptoms against to serotype 2. So that's why uh, some of the countries are licensed this one, but it shows some side effects in the children. And then Qdenga was approved by European Medical Council, which is produced by the Takeda company, and it was approved in the December 2022. So year back it was done. Its efficacy for the dengue 1 and 2 is good, but more than 70%. And dengue 3, 4 efficacy are not known because of the circulation of dengue 3 and 4 cases are low in the society. That's the reason why Qdenga is still not approved by the maybe FDR. What is going on? I don't know exactly. So the dengue virus risk areas you see even in the global virus, so the South American countries and these Middle East countries, Eastern countries, even India and other Eastern countries also affected by these dengue viruses. So this is major countries are affecting throughout the globe. So even in the America from North America from 2003 to 13 or 14, as per the CDC result, CDC report, it shows more than 10,000 cases from 2003 to 13. After 2013 to till now, there is only 1,000 to 2,000 cases are reported each year. We can see that because of here the clean environment. I have not seen even single mosquito here from last 3 years. I'm staying in US, but that's the beauty of US. Here we could not get these mosquito borne or like it's a very clean city. I appreciate that. So in the city wise, so later on, that what are the challenges in the making the dengue vaccines? There are 4 serotypes which are close sequence homology or sequence similarity, antibody dependent enhancement, different conformations in the mature, immature state, and partially mature state, and bumpy particles. And it needs to give as a tetravalent vaccine, and it should elicit for all 4 serotypes equally in a person the immunity. Then only it will protect from the dengue viruses. So how these dengue 4 serotype look like? They look like same structure wise. So you can see this dengue 1, dengue 2, dengue 3 and dengue 4. They look like same, but they have sequence homology expansion from 7 up to 75% sequence similarity. Each serotype has a many genotypes. Within the genotype, the sequence similarity changes from 3 to 5, varies between 3 to 5%. Due to these sequence differences, even the person got infection with one serotype, that's not going to protect for all 4 serotypes. See, let's talk about ADE. What is ADE? Antibody dependent enhancement. So when the person got infection with one dengue serotype, the person will develop the protective immunity for that particular serotype. So that is a primary immune response or get the cure from that infection. When the person got the secondary infection with the same serotype, he will have already immunity for that serotype, and our body will protect or save from that infection. That's called as a protective immunity. If the person got the secondary infection with a different serotype, that will the primary immunity or primary antibodies goes and binds on those secondary serotype, and it says it mimic the immune system, and and enhances the infection by by helping the virus entry by the Fc gamma receptor. These antibodies are subneutralize these viruses, and using these antibodies, Fc gamma receptor binds to these antibodies and helps in the virus entry into the cell. That's what increases the risk area on replication of the virus. So that's ADE. So let's talk about what is the different shapes of viruses in the immature state, bumpy particles and smooth particles, as I mentioned in the challenges. So here, when the polyprotein is processed, we will first get these envelope proteins in the PRM is not cleaved by this furin protease. That's why you will see trimeric envelope protein with the PRM. So you will see 60 spikes on the virus, so each of them are the trimer, and when the furin act on these furin proteases and it cleaves, then in the trans-Golgi network you will see furin is detached, furin is cleaved, and you will see a furin peptide is still there, but you will have 90 dimers, PRM dimers. When the furin is again cleaved, you can see PRM dimers here. Once it changes the pH, the PR is detached from the E protein, then you will have 90 only M and E protein dimers. So these are arrangement in the like whole virus envelope, how these are arranged on the envelope. PR is detached. PR is the protein which again shows the immunity, like our immune system is going to against act on those PR peptides, produces the antibodies. These antibodies, when the infection occurs, the dengue infection occurs, binds and helps in the infection, increases the rate of infectivity, subneutralizes within the genotypes also. That's why PRM should not be there in the vaccine candidate. We have to remove PR peptide from the vaccine. So these are the different shapes and different maturation processes of the viruses. Now I will talk about the structures of the dengue viruses and the receptor, where it is binding, and what is the importance of these attachment factors and receptors. So I saw this recently. This structure was solved even earlier also in 2006 by the Richards group. Still, as a control structure, I have done recently. There is a 3.5 angstrom resolution, a dengue virus structure. So it's here. It is the map. Here is the map. You can see clearly in the asymmetric unit. I just marked with this triangle. Here it has a 5-fold axis, 3-fold axis, and 2-fold axis over here. It's in the icosahedral symmetry. Each asymmetric unit has a 3 M proteins, 3 E proteins in the heterodimer form, and it is total the envelope total virus surface is covered by the 180 envelope proteins, 180 M proteins. The differences between these dengue virus envelope protein, other flaviviruses envelope proteins, is that so these envelope proteins has extra N67 glycosylation site in the domain 2. The envelope protein has a 3-domain structure. One is domain 1 is in the red color, domain 2 is in the yellow color, domain 3 is in the blue color. M protein is in the shine color here. Here in the salmon color. These are the cyan color one are the E protein transmembrane helices. So these glycons are the extra glycosylation sites in the dengue viruses compared to other flaviviruses. Other viruses has these N153 equivalent glycosylation sites, N153 equivalent sites in the domain 1. So how does the dengue virus enter into the host cell? This was the biggest question when I started this project in 3 years back in 2020. 2021 May 14th, I think I joined here, and I started this project in the June, so 2021. So how these dengue viruses are enter into the host cell, what are the key receptors and attachment factors for the dengue viruses? So that's what my target here. In the literature, I saw many proteins or says These are the receptors, act as a receptors for the dengue viruses. One is a GRP78, mannose receptors, heparin sulfate and heparin, TIM-TAM complexes, HSP90 and 40 proteins, 70 proteins, NKP44, DC-sign proteins. So out of all these, this heparin was known or reported more than 1600 times. Heparin is a attachment factor for the dengue viruses. In the literature, tremendously they reported and shows that it has a high affinity for the dengue viruses. And the DC sign is also binds to the one of the glycan on the dengue viruses. That's what reported. Then I checked this, and where it binds exactly in the dengue virus structures. So people have predicted in the different sites where speculated, and they are publishing. So I attempted for the dengue virus a heparin structure as well as design structures. Here you can see, I will give you a brief introduction about the heparin as well as design. Heparin is a ubiquitous molecule composed of uronic acid and glucosamine, and it has an attachment factor for the synbase, triple EV, SARS-CoV-2, HC, many viruses. Design is a C-type lectin and type 2 transmembrane protein. It binds to mannoses on the pathogen glycans. Design is a receptor for the hepatitis C, dengue, and human immunodeficiency viruses, Ebola, and many other viruses. In this, design is a tetrameric molecule in the native form or the cell. So it has a cytosolic tail, transmembrane protein, and the neck domain. Neck is the major place. It has a 7.5 equal repeated sequences, and it helps in the formation of the homotetramer. And the carbohydrate recognition domain, which recognizes the mannose sequences on the pathogen glycosylation sites and helps in the virus entry. And this cytosolic tail has a endocytosis initiation signal sequences. So this is the overview of the disease and structure. So when I tested this heparin inhibition for the dengue 1, 2, and 4 serotypes, dengue 1 and 2 are completely inhibited at 10 microgram per milliliter concentration, and heparin was on dengue 4 even at the 100 microgram per milliliter concentration also, still it has some infectivity due to maybe the heparin binding site is not that like the affinity for that site is not efficient. There is a minimum number of positive charge residues in the dengue 4 serotype compared to dengue 1 and dengue 2. Dengue 1 has a more positive charge, dengue 2 has compared to equal positive charges, but it has lysine residues and arginine residue differences. That's what I saw. And where it is binding exactly on the dengue virus structures, so I saw it is binding exactly on the envelope protein domain 2. Here you can see clearly the stretch of how it is binding. This is the heparin molecule on along the raft. Each envelope protein is map, and here it is a model, and here it is a difference map. We can clearly, when I subtracted the native structure with this structure, we can clearly see only you have heparin density on this structure. So each strip is equals to 6 heparin molecule. Each heparin, okay, this is the heparin, how it binds, where it is binding on the dengue viruses. Later on, as I mentioned, a DC sign is a tetrameric molecule. It is also inhibiting the dengue virus entry into the host cell. Dengue 1 is inhibited up to 75%, and dengue 2 is inhibited 70%, and dengue 4 is inhibited 90% of virus entry into the cell in presence of DC sign. So where it is binding on the exactly structures, here binds again in the heparin binding site. As I mentioned, dengue viruses has envelope protein has extra N67 glycosylation sites. There it is binding, conjointly binding, not as N153. So we can clearly see N67 is the binding site for the DC sign. Yes, this is the map, this is the model structure. So we can see all 180 envelope proteins are occupied with 180 carbohydrate recognition domains of the DC site. So it is strictly binding to all N67s. So here, yes, now both the structures, in the both the structures we have seen attachment factor and the DC sign is binding in the same place, whether they bind simultaneously in the same time, or they bind, one binds and other one is compromising like that. So I tested the structure. Yes, it is binding both in the adjacent receptors. Heparin binds on the surface of the envelope protein, interacting with directly interactions with the envelope protein residues, amino acids, side chains, and but the heparin this design is protruded or binds to the distal end of the N67 managers. So, but they bind together. They are important. So they are binding. That's what here in this structure we got it. So when I remove the heparin from the cell surface, what is happening? When I remove the glycans from the cell virus surface, what is happening? So here when I remove these heparin from the cell surface, infectivity of the dengue 1 is lost up to 75%, dengue 2 is lost up to 90%, or dengue 4 is lost up to 60%. So the dengue 1 glycans completely lost here, and here when I remove glycans, it has a still 10% infectivity. Here it has a 15% of infectivity. If you remove both heparin from the cell surface, glycans from the virus surface, it is completely diminish the infectivity. That means the virus, for the virus infection, you need both heparin as well as a decycline for its entry into the cells. So how, as I mentioned in the while introducing, the design has a cytosolic endocytosis signal sequence. The signal sequence is so I tested two types of endocytosis. One is clavulin mediated and clathrin mediated endocytosis by the using inhibitor nystatin and CpG. Nystatin is the clavulin mediated endocytosis inhibitor, and the CpG is a clathrin mediated endocytosis inhibitor. Nystatin does not affect the dengue 1, 2, and 4 infectivity, and but the CpG is completely inhibit the virus entry into the cells. So that says clearly it is enter into the cells by the clathrin mediated endocytosis signal sequences. So with this, I would like to conclude my talk. So cryo-EM structures of the dengue 2 heparin complexes reveal the heparin binding site in all 4 serotypes, and high resolution dengue 2 structure in the complex with receptor design shows that the design binds to N67 glycans. Cryo-EM structure of the dengue 2 complex with both heparin and design show they bind in the adjacent binding sites at the same time. Inhibition assays showed that lack of heparin as on the cell surface and the glycans on the N67 resulted in the loss of infectivity. With this, I would like to thank Professor Richard and all the lab members, particularly Thomas and Andre, who helped me in the data processing, data collection, and all other lab members directly, indirectly. They supported me a lot. Without their support, I'm not able to do all this work. So they are. Everything is in the right track, right path. They keep me everything in the right place. So that's why this much productivity is happened in a short time in the lab. So I would like to thank Purdue University for opportunity and biological sciences and cryo facility from the Purdue. So and NIH grant supporting for this project. At last, I would like to thank my wife and son for their constant support and motivation and keep me happy all the time in the while doing science. So that's what. Thanks, Tommy, for.
Excellent. Well, thank you so much, Venkat. I think it's awesome to see this journey and how far you've gone. I thank you also for a great lecture, great science, and it's always awesome to see that type of progress and that type of productivity. So thank you, Dr. Venkata Are from Biological Sciences at Purdue University. Thank you for being our lecture hall series speaker today. I hope you have a great rest of your day.
Yeah, thanks, Tommy.
Bye-bye.
See you. Bye-bye.
Thank you for watching the Purdue Lecture Hall series. Remember to hit the like button and subscribe to our channel.